Today we're going to explore the question, how can we use very rapid rotating stars to measure gravitational waves? By the end of this talk, you will know what are gravitational waves, what are pulsars, how pulsar timing arrays work, and how we can use them to detect gravitational waves. And you will also know nanographs, evidence of the stochastic gravitational wave background. But first, let's go back in time a little bit. The human race has always been amazed by the night sky. So we built simple telescopes like Galileo's to observe the stars. But that wasn't enough. So we built bigger telescopes, like, for example, the Keck telescopes, which I believe are at this time the biggest ones. Now we can measure wavelengths that our eyes can even see. But guess what? That's not enough either. So now we want to detect gravitational waves, which are deformations in space-time. They are not even light anymore. And for that, we built interferometers on Earth, like LIGO, but also we have plans to build them on space, like LISA. But you don't even know what are gravitational waves exactly. So let's start with that. Gravitational waves, let's think of them before as a fabric sheet. Imagine that space-time is a stretchy sheet, and you put a massive ball in it. The ball will fall down and bring the fabric with it, just like the first picture. This is what happens in real life. The theory of general relativity by Albert Einstein predicts this behavior, and it says that concentrations of mass energy can and will deform space-time like this. And also, when we have an uneven change of this concentration of mass energy, it will form a propagation of a wave that will deform space-time, like the animation you see over there. That is a representation of a gravitational wave passing through our sheet, our fabric. Because they are not blocked by anything in the medium they go through, they are great sources of information from the environment they were created. And some of those environments are, for example, binary systems of black holes or neutron stars because they are very dense. And when they are merging these binary systems, they create that uneven environment that we were talking about earlier. We also have supernova explosions because they are very violent phenomenon, and because of that, they also create that asymmetrical distribution of mass. We also have rapidly spinning neutron stars with small bumps, which are the mountains. I think you know a little bit what pulsars are, or neutron stars, and they spin. And because of this spin in the off-axis rotation, the bump will create an uneven distribution of mass. And we also have some theories of gravitational waves that come from the early universe. Oh, sorry, I will explain a bit more. Because it is believed that in the early universe, there were some extreme phenomenon that also created gravitational waves that are still present nowadays as a background. Just like normal waves, these have some properties like amplitude, frequency, and the strain that we can measure based on what they do to the matter. And these properties depend on the source of the wave. For example, when these waves are created by binary systems, the amplitude increases with the mass of the system. Still, with the biggest binary systems we can have, with the greatest mass, the effects of the gravitational waves we detect are very, very small, as we'll see. To detect these effects, we use interferometers. And the biggest example is LIGO, the Laser Interferometer Gravitational Wave Observatory. It is built of mainly 4-kilometer long arms with mirrors at the end. And these mirrors are what detect the change when a gravitational wave is passing through Earth. Now, with 4-kilometer arms, we can detect a gravitational wave effect of approximately 1,000th the diameter of a proton. So, like I said before, it's a very, very small effect. Imagine 4 kilometers just for something smaller than the diameter of a proton. Still, With this experiment, we have made huge discoveries. For example, on September 14, 2015, we made the first direct detection of gravitational waves. And we also confirmed the existence of binary black hole systems, which were only theorized before this. We also observed that they can collide and merge, and that's how they produce the gravitational waves that we detected. Also, this time together with Virgo, in August 17, 2017, we detected the first gravitational waves from the merger of binary neutron stars, but this time we also detected the light emitted from it, which is a huge achievement because this event is a primary site for the formation of heavy elements, which is a question that has been open for decades. We can talk about it later because it's a whole other topic. Now, because building interferometers on Earth is not enough, we also have plans to build an interferometer in space, which is set to launch in 2035. This time we will measure the frequencies from 0.1 millihertz to 1 hertz, and the sources are a bit different. Now they are from merging supermassive black holes, binaries of compact objects, once again, but also the early universe. So this time with LISA we will measure frequencies in the low range, while with LIGO we were measuring from 10 hertz to thousands of hertz, which is a high frequency range. But today we are not going to talk about interferometers especially. We are going to talk about another option to measure gravitational waves, which is pulsars. So what is a pulsar? It's a rapidly rotating neutron star that results from the collapsed remains of massive stars after a supernova. Its period, it's very well known because, as you can see on the right animation, it emits a beam of electromagnetic radiation that we can detect here on Earth. So we can measure its period. Now, pulsars are born with a period of approximately 10 milliseconds, but they naturally spin down to 0.1 to 1 second. This decrease in angular velocity is due to the light or energy emitted by the beam light. Now, in a binary system, mass and angular momentum can be accreted from the companion star, spinning the pulsar back to its original period. One thing about the millisecond pulsars, the title, is that they are usually in binary systems. So these are the ones we are going to care about. And this process that I just described is the recycling of a pulsar. And it's very good because it can stabilize its period. It also decreases the magnetic field, which decreases the spin down rate. So this gives the millisecond pulsars a precision close to atomic clocks. And why is this important? We will see later. The timing that the pulse from a pulsar takes to reach Earth can vary. Even though the pulsars are very precise, there are many factors that can affect this. But one of them is gravitational waves. As you can see in this image, a gravitational wave is disturbing the space-time, and the pulsars that were originally at the same distance now the light from them has to go through a different path. Now, gravitational waves can shorten or uh, how do I say it? Squeeze or stretch the space-time. So the time that the light from a pulsar will take to get to Earth will increase or decrease. And the difference between the expected time of arrival and the actual time of arrival is called the timing residual. And by analyzing the timing residual, we can see if there was a gravitational wave passing through. Now, these timing residuals affect the pulsars in a correlated manner. For example, two pulsars that are close together will be approximately at the same point of the gravitational wave. So they have approximately the same effect. However, in another point, the gravitational wave may be shortening the distance instead of increasing it. So you will have a different correlation. And that can be predicted using the Helling-Zahm's curve that comes from the theory of general relativity by Albert Einstein. So basically, what this does, is describe the theoretical correlation between the timing residuals of two pulsars as a function of the angle between their positions in the sky. And this is one of the best ways to identify if the timing residual is due to a gravitational wave or not. The other way is to see if the timing residual presents it presents the quadrupular pattern. The other two are not from a gravitational wave, and we will see why. The monopolar pattern is basically when the pulsars show the same timing shift in the same direction at the same time. This is basically when you have your clock set 2 minutes ahead, so it's basically a calibration problem. We also have the dipolar pattern, when pulsars in one region of the sky show timing shifts in one direction, while those in the opposite region show the opposite shift. For example, if we have Earth wrongly centered, for example, we have Earth here, but we are here, this will be wrong, and this will be wrong as well. So this one will actually take a shorter time than we predicted, and this one will take a longer time than we predicted. As I said, different directions. And we also have the quadruple pattern, one we are looking for, where pulsars show a four-lobed correlation pattern. Some pairs are highly correlated, some anti-correlated, and others not correlated at all. But it is also corresponding to the Helling-Zahn curve. Now, we cannot just pick a pulsar and just say, okay, we will see if there's a gravitational wave passing through. We have to study it for a long time. A millisecond pulsar can be included in a pulsar timing array, which are the group we study, only after being monitored for at least 5 to 10 years, with a timing precision on the order of 100 nanoseconds. This is because, even though they are very precise, they still present some timing noise, which we will talk about later. And we have to know it so that we can extract it from the predictions we make about the gravitational waves. And also, the frequency range of gravitational waves accessible to the pulsar timing array method is determined by the total duration of the dataset and the cadence of pulsar observations. Currently, this range is roughly in the nanohertz and 100 nanohertz. However, if we continue to do this research, we may be able to increase this range. As I was talking about, we have some factors to account for due to the timing noise. The first one is intrinsic to the pulsars themselves, and is pulsar jitter. Although, for example, millisecond pulsars are very precise over time, each individual pulse is not necessarily similar to the next one. So we need to study them over time and then integrate them and use them as a group. We also have clock discrepancies, which may seem irrelevant or at an amateur level, but the thing is, we are talking about nanoseconds precision here, so the time we have at the telescope and the international time, of course, matters. We also have some other factors, which are the dispersion delay, which has something to do with the delay in time for the radio waves to get to Earth. We have the Raman delay and also additional relativistic time delays, which actually can occur twice if the pulsar is in a binary system, which is just a fun fact. Now, on the right here, we have the Green Band telescope, which is one of the most important telescopes for this type of research and is used by NanoGrav, the North American Nano-Earth Observatory, known for specifically this research that I'm talking about today. And in June 2023, they presented their 15-year data set, and this is the most important result they got to. The evidence of the stochastic gravitational wave background. So, we don't always measure just one gravitational wave. Actually, we can measure a background, which is what happened here. As you can see, the dashed line is the Helling-Zahn curve, the predicted one. And the dots in blue with the uncertainty are the data points we got, which are similar to the Helling-Zahn curve, still with some uncorrelations, but still. And also, we have a line at 0. That's what we would have if there were no gravitational wave background. So, NanoGrav, the organization I was talking about before, affirmed that Even though we are not at the value for a definitive discovery, we are still very close, and they affirm that this is very much unlikely to be a random event. So they are pretty sure of this gravitational wave background. Also, two other organizations did separate research, which is the Parkes Pulsar Array and European Pulsar Array, so different pulsars. And they got the same conclusion. So with this, we have studied some gravitational waves, some different types, based on their frequency, characteristic strength, and sources. With LIGO, we researched some gravitational waves from around 10 Earths to thousands of Earths, and that come from events in the nearby universe. Not so big, but very rapid events. Now, with the pulsars, we are studying gravitational waves in the nanohertz, so the very low frequency range. And it's most likely from the, also I didn't say this before, it's most likely from the merger of massive galaxies and the supermassive black holes binaries. It's a very long name. And we also have plans to study a different type of gravitational waves with LISA. And then we will see gravitational waves in the range mainly from 0.1 milliards to 1 Earth. But still, we are a bit far from that. Now, we have to give credit where it's due, and that person is Albert Einstein, because gravitational waves are not something that we look at the sky and they are there. Actually, they came from math. They came from his field equations, which is something I find truly fascinating because this is a solution. Just like black holes, gravitational waves, and also wormholes, if you know what that is, were solutions to his equations. Just one, actually. And at the time, they were just theorized, but till now, black holes have been proved, gravitational waves have been proved, some others have been proved as well. Wormholes, not yet, but none of these solutions have been proven wrong. And I think that is truly amazing. But the most important part is through math, we got something that is physical. So I think you should really think about that. It's truly amazing. But that was my presentation. Thank you.